Now we'll have a presentation from another trainer, also from the previous days already, and main contributor also to the material that we have online from this workshop, with Marcelo, who's tuning in from Germany today, originally from Brazil.
Yes. Hello, everyone.
Hi, Marcelo.
Good morning, good afternoon, good night. I don't know.
We're very excited to hear from you about the Napari clusters plotter.
I have a small presentation and then I'm going to do a live demonstration of the plugin. Yeah, so I prepared some slides to, I think it's good to give some motivation. Can you all hear me? And I think
Yes, it's perfect.
Yes. Okay, good. I don't know if the Zoom stuff is on the way. If it is, please let me know. I can try to make it disappear. Yeah, so today I'd like to present an Napari clusters plotter. I think it's, if not the most famous, it's one of the most famous plugins that our group has developed so far. And it has, I think this the screen that the animation that it's often shown, like, so I already give you like a preview of what's coming up. And if you want to try today this live, let me just hide floating panel. Yep. The version that is installed in the environment unfortunately had some things that we recently fixed. So in case you want to try it today, I'm just leaving a small 2 lines of commands here to like install it in a new environment. And this is also in the PDF that I just uploaded to the GitHub repository. I'm going to paste the link to the chat soon. So this is a nice project that involves contribution, open source contribution from different groups. So if you can see here in the, oops, if this animation starts over. So this project's, this is like the history of contributions to it. And it started with these 2 outstanding master students we had in our group, Laura and Ryan. And then, of course, there were contributions from Robert. And then, interestingly, sort of recently, Thorsten Wagner is a group leader at MPI in Dortmund, joined in because he had some ideas. He had some code already to implement some stuff, and we were going in the same direction. So it was like a very nice match. And I think that's how open source contributions from different groups happen. And of course, Scikit-Image is a much larger example of that. That's just to show you how this plugin started. I want to give just a small step back to highlight the potential of having a bioimage analysis workflow together with the visualization. So we are all interested in quantifying our images, like we can segment some objects and then measure some of their properties. But it's really nice also to have like this visualization around. So just from a table, we can readily see, like click on each object and see alive, like what's its area or other properties. And Napari is one of these tools that allows us to do that very nicely. And this is good because we want to rely on computers to do the analysis for us because, yeah, they are more trustworthy than bias from person to person, for example. So most of the times we look for algorithms that could do the analysis for us, also to save time, of course. But having the visualization helps us gain some trust into these automated methods. So if you see this image, you can say, okay, the algorithm may just say this image has 65 objects. But if you really show the segmentation results with different colors, this may be a bit better to really trust that it's doing the proper job. And even better, like if you put some number labels on top of it, then you can gain more trust that's actually done the counting well. And besides that, we may have like as a result of some segmentation methods, and we may want to further classify those objects into different classes. This is also called semantic segmentation. And we could do that with the according to an expert's annotation, for example. So somebody could tell, okay, these groups of cells are different from those. And then we let a machine learning try to figure the class of the other objects for us. And the clusters plotter does not rely on that. So we rely on an unsupervised separation. So this means that we do not provide any manual annotations, and we let the statistics of the objects themselves separate, be used to separate these into multiple classes. So that's what this plugin is about. Yes, and then, for example, as I said, unsupervised machine learning means that we take measurements and we do not label data. So imagine we taking like 2 measurements of objects like roundness and aspect ratio. So we can collect like from different samples, we get different measurements of these 2 objects. And then once we collected enough, we can, for example, check the marginal distributions or the histograms of those. And then what these algorithms may do is they typically rely on these statistics, and then they can find like some groups based on that. So, and that's interesting because that changes a bit. That can change how we ask our hypothesis, our biological question. So imagine we have a hypothesis that we could say like a cell shape can be influencing by modifying parameter X. So you do some kind of treatment, and then you expect the cell shape to change. So we start, for example, with a null hypothesis, and we must choose some sort of shape measurement, maybe circularity. And then the null hypothesis would say like circularity of modified cells is similar to the control group. Then you can prepare your sample, go to the microscope, you acquire some images. And I'm going very fast, but of course, these steps may take a very long time. And it's also self-segmentation. You try to do it as best as you can. Then you get some circularity measurements, and then you have some statistics about it, and you compare. But then you may wonder, like, okay, maybe they do not differ very much. Maybe circularity is not the right parameter to measure. I'm not sure. Maybe the segmentation algorithm should have been different. You should try that. Or maybe you should try like I don't know, a confocal, but another type of microscope. And then the idea here is like, maybe we start this question differently. So we could start like, which of image-derived parameters influenced when I change X? So we do not assume it's going to be shape necessarily. Then you could also do like your sample preparation imaging. You could try different segmentation algorithms, and you could measure a bunch of stuff, like all the features that you can get from these objects, and then also calculate statistics. Then your question could be, which of these parameters show a relationship with X? Also, you could also argue which of the algorithms of segmentation can show a relationship with X and Y. If you do that, what you end up having is a bunch of, as I said, a bunch of properties. So we could end up with a table where you have like, you may have 2 different groups that you expect them to be different somehow, and then you have many statistics. So the problem of here is that each of these columns represent a different dimension. So we have like a very high dimensional problem. And it may be hard at first to tell which of these features reflect the biological properties. So you could look at them individually, but you could also do dimensionality reduction. So dimensionality reduction means that the challenge is to find a representation of all these dimensions that can be represented in a smaller dimensional space in a way that you could, as best as possible, like preserve their relationship. So yes, you may be able to preserve local distances at the expense of global distortions. So as you can see here, so yes, maybe global distances may be distorted and maybe local distances can be preserved. But this transform this multidimensional number of features into just a 2D plot. And then one of the algorithms that we have implemented in the Napari classes part is the UMAP. So here's a small example just to get in our heads first. This is from a region here near Dresden. So if you consider that you would like to go from this small village Wellen up to Strand, you could just consider like get the Euclidean distance. So the easiest way would be to go from P to point Q, because this would in theory take longer. So here we're just considering like the distance when looking from the top. You might have another property like you want to take into account, like you may have to take into account travel time while you're hiking. And then what you maybe do not know here is that there is a big mountain in between here. So actually going from P to Q directly, even though it looks it should be easier, if you take into account that the travel time, then it may be actually be faster overall to make a quick stop into Hatton and then go to Strand. So I mean, maybe the data might be better represented like this. So taking the shortcut to A may be faster. So that's what we mean by when you give like other dimensions to try to get the relationships, you're basically distorting a bit how they look. And UMAP tries to do this connection. So here I got an example from how UMAP works, just to try to explain a bit. I'm not a UMAP expert, but I hope I can do my best to show its principles. And here is an example of how you could reduce the dimension of a 2D, in this case, it is said to a 1D. So we can all see the pattern there, but from the computer, it just sees like points. It's not entirely clear at first that this should have the pattern that we are all seeing. And then one way that it could do to try to connect these points and see their relationships could be like to establish like define a small radius around them. And then, then if they touch, then you can connect them. And then you could try to get a pattern of what you have. The problem is that you may end up with, usually you have some scarcity in your data, so you may end up with disconnected regions, and then it may be difficult to get the whole pattern. So what UMAP then does, instead of putting a fixed radius to each of these points, it lets each point have its own radius of search, and this radius will depend on, I don't know, up to which neighbor you want to go. So in this example, the radius goes as big as it can up to the point that it can get like 4 neighbors. So this means that from a point of view, the distance, and it considers like all the radius as having radius 1 when you are considering the central point. So the distance from A to C, from A point of view, is 1. And the distance from C to B, from C point of view, is also 1. So each point has its own coordinate system now. This allows you at least to connect most of them, but still some of them may be isolated. So what UMAP actually does to ensure that all points are connected, it assumes, so it gives like a fixed radius up to the next closest neighbor. So with this premise, all points will at least be connected to a neighboring point. And then from then onward, it's like a fuzzy topology. So it means that it's not like a yes or no anymore, but like a fading away weighted connection. And this allows it to give different ways to these connections. So if they are just strong neighbors, then you have like some highways connecting them. And if they're sort of far away, they will have a low way connecting them. And then, I mean, you can, with this, you can connect all your elements, and with the ways, you can also optimize some cross entropy function of these ways to find the underlying lower dimension pattern. So this is an example like how you could show from a 2D get into a 1D dimension. But in practice, what you see in the plugins is that we are usually getting ND dimensions, depending how many properties you measure, and going down to a 2D plot. After you manage to reduce all your features to 2D, you may want to cluster them. So here, it's like a result from the UMAP over different features in a 2D plot. And then, like in this feature space, it reveals groups in our data. So is there a way that we can identify these groups? And that would be clustering. So clustering allows us to stratify data into groups without also previous annotation, similar to what I showed before. I'm just gonna explain one of the algorithms today, which is the k-means clustering. So the k-means would group these data points into n groups, so the variance within groups becomes minimal. It starts like with seeding like 3 random points, and then dividing these spaces around these 3 initial points, and then all the data that's within that region gets that class assigned to it. And then there's, of course, an optimization process where it changes the center of these regions up to the centroid of the data inside it. And then it repeats itself up to convergence. So the effect that you have is basically what you see here in the right. So it ends up converging to some centroids of clusters. And the strength of this is that, I mean, the strengths and weaknesses, because you need to feed it with the number of clusters. So you have to say, I'm expecting to find 3 clusters here. And the clusters cannot capture more complex topology. So like if you get just agglomerated pointers like this, it works very well. And then for other types of relationship, maybe you have to use a different clustering algorithm. And it's good that it's based on Euclidean metrics. So if you get new data, then every new point can be assigned to one of these clusters. So the clusters plotter, as I said, showing here, Laura and Ryan starting developing them. And it can apply a few dimensionality reduction algorithms like PCA. It also has TSNE, and the one that I just mentioned, the UMAP. And after doing the dimensionality reduction, you can apply some clustering algorithms like the k-means cluster. That's the one I just mentioned. They also have agglomerative clustering and HTP scan. What's also nice is this data exploration part. So besides using these algorithms, you could also use it yourself to manually highlight this clustering. So you can do like manual clustering, and that then have the visualization back in your data. And you can plot different features there, not only the UMAPs, you could also plot yourself like the area or density. And that helps you hopefully helps you get a better understanding of the relationship of the features that you're measuring in your data. Yeah, so those are my slides. So the exercise, like this demonstration, I left some general instructions here, but I'm going to do them live with you. I just leave it here because then you can check in the PDF later. And basically the first steps are just some general steps up to get to the point where we have like some segmentation with some features. And then the 3 last steps is actually applying dimensionality reduction, clustering, and also visualizing it back. I would like just to leave a reference for a nice article that shows how you can explore your data using the clusters plotter. So take a read there. It should contain some of the stuff I'm going to be showing today. And yes, I'd like to thank my group for for developing and then helping maintain this nice plugin. And yes, then thanks everybody. So here I'm going to go to File, and I'm going to use for this demonstration one of the examples here from Napari. So I'm going to open sample Napari and human mitosis. And here we have some fluorescence of nuclei. And now I'm just going to apply like segmentation algorithm. So I will be using the Voronoi-Otsu labeling algorithm. So you can find it in the tools menu, segmentation labeling, Voronoi-Otsu labeling. It's also available via the assistant. And then here, I'm just going to choose some values that should be fine. And then, I mean, we have like a segmentation of our nuclei. Then I'm going to, then I'm going to, so here we have the result of segmentation, but we did not get any features yet. So we can get that also via the tools menu. If you go through measurement tables, there are a few options where you can do that, and I'll be using this object features properties, which should like open this small widget, and then you can select like which features you want to measure from these objects. And here I'm going to take in some intensity measurements, size, and some shape measurements. Then if I click on run, then a table pops up either in another tab of the right side of your window. And here you can see that like we have the labels and the label numbers and all the properties here. So one could also save this table as a CSV and also continue working from there. I'm going to close it. That doesn't mean the table is gone. I just close everything. So once you do that, the table gets saved within this labels layer here. So the information is still there. What I'm going to do now, let's do some plotting. So before we even do dimensionality reduction, you can see some features. So I go into under tools and visualization, and I want to plot measurements. Then this is the plotter from the Napari clusters plotter. And here you have labels layer. Then this labels layer should refer to a labels layer containing the features. And as I showed, you just have to do the previous step to get those features there. Then they should show up here. And you can choose like what you plot. So we could plot, I don't know, area versus intensity. We could see if there is a relationship, for example, the bigger the nuclei, the brighter they are or something. So here's just exploring. And you can already do some manual visualizations back. So let's say I just want to get the bigger nuclei. So I could just do a drawing here. And then, I mean, these points are highlighted back in the image as a new layer just for our visualization, right? If I just click, then this selection is gone. So I can do that again. So these are like the biggest elements. And if I want also to see the brightest elements, those should be here on top. At the same time, I can hold the shift key from my keyboard and then do the same. Let's say do this. And then they are shown in a different color. If you do not hold shift, then they will also be blue and these will be gone. But the shift allows you to keep expanding the number of manual clusters. So here I'm basically doing it manually. And you can see here the clustering method is now assigned to manual cluster. Yes, now if we go, I can close the plotter at any time. Can reopen again if I need it. I will run the UMAPs for this data. So for the clustering and the dimensionality reduction, you should find it here into measurement post-processing. And then you have both here. Then in dimensionality reduction, we also have to provide, as usual, the labels layer with the features. So it's this one by the name. And then here we're going to choose UMAP. Yeah, so there are some parameters from UMAP that you can choose. We want to have this as two components, so you can plot it into the 2D, into a 2D plot. Here you can select which measurements you want to apply it. For example, I can click and hold Shift and go up to the one I want. I can put them all if I wanted. I will stop at the standard deviation intensity. Because there was a bug we just fixed it this morning, but the Conda version is still in the oven. So it's just that these three measurements may have infinite terms, and that could lead to errors. So that should be soon fixed, but fortunately for right now, I will just not put them in. But I will do a dimensionality reduction of all these other properties selected here. And then this is the one which may take some time. Let's see. Okay, so after this amount of time, the table pops up again just to show you that the UMAPs were computed. I will, so it's very normal to like close these widgets and reopen them later because of course this right side becomes so full of stuff. So I will be closing the dimensionality reduction just to see my table better again. Then if we scroll up to the very end, now we see we have two new columns, which are the UMAP 0 and UMAP 1 components. I will close it, no harm there, because it's, as I said, still saved. And now I'm going to apply some clustering to that. So I will go now to measurements post-processing and clustering. And then here, as the part where Rocco suggested that we tried that in a bit. I just follow the previous instructions for now. I did not try to put multiple dimensions here, but here you can select which properties you want to cluster. And in this case, I'm just selecting UMAP 0 and UMAP 1. And here you can choose the clustering method. So k-means. I will, as I mentioned, you have to provide like how many clusters you expect. So I will suggest 3. And why not standardize these features and run? So yes, so the table pops back again. I'm gonna close this. And then if you see at the very end, we have a new column, which means which is the values of the clusters. But that's not very interesting to see here. So now that's the part where we can go back to the plotter. So I go back to tools, visualization, plot measurements. And here I now have some extra stuff. So I'm going to plot first UMAP 1 versus UMAP 0 versus UMAP 1. So this is the result of the dimensionality reduction. So all the other features are somehow depicted into this 2D plane, preserving as best as possible their local connectivity. And we can visualize the result of the k-means clustering by selecting it here in the clustering method and clicking on plot again. Now we see that that's the result. So that may hint us that these groups may be different for some reason. And what is also interesting is that we can now, because we already have the results of this, we can now go back and look at other relationships. So maybe we could, let's see, try to plot again the area here. So of course, in plotting area versus map 0 may look weird a bit, but the area seems to be The clusters does not seem to be very different regarding area. We can also look at area alone. And that doesn't look very helpful, but there is this expand for advanced options button. This is sort of recent, and then we can see this as a histogram instead of a scatter plot. Now we're just seeing like the histogram of the area, and we can still see the colors of the result of the k-means into this histogram. And of course, if we go back to 2D, then I would have to plot the area against something else. So maybe area against mean intensity. So if you have like a lot of elements, then showing as a 2D histogram may be more interesting than showing as a scatter plot, because then you don't see the points on top. I'm just going to click here outside. I have to hide non-selected clusters. So this is like area versus mean intensity shown as a 2D histogram. And as a scatter plot, we've seen that at the very beginning, right? Yes, but sometimes showing it as a histogram may be more insightful, and we can put back the result of the k-means to see where these groups fall. Interestingly, the blue group seems to be bigger nuclei, and yeah, the intensity, it's a bit everywhere, right? So I think I'm gonna stop right here. I could maybe try try what Rocco suggested, put some extra features to the clustering, and then see how it goes. So let's say I want to cluster area. Let's start with 3. So k-means. But the problem, yeah, let's see. So it does work. Yes, let's visualize that back. Let's go back to the plotter. And then, I don't know, we could see area. It's hard to see what would be useful here. Also, if you have any hints. Yeah, so I mean, this is the result. The colors are the result of clustering UMAP 0, UMAP 1, and area. Doesn't make much sense, I guess, because we used area as one of the parameters to get to the UMAPs, but at least you can see that that's possible as well. But then to visualize is a bit the challenge, right? You can only plot two features at a time. Yes, I think that's what I want to show. By the way, well, if there are no questions, I just can say that as you saw in some GIFs, this also works for 3D. And if you have features over time, you can also see them over time. And then the current time point is going to be highlighted here as a bit of white dots. So you can also see a bit how this changes over time. And I just chose this 3D example because it's faster to show it live.
So with that, let's thank our speaker one more time. Thank you very much, Marcelo, for introducing this useful tool to us.
You're welcome. I just going to leave the link in the chat to the plugin webpage in case somebody wants to give it a try.
Excellent. Thank you very much.